Okay, so we are going to continue on in chapter 9 here, and we left off by finishing up creating or constructing a displacement diagram based on a motion sequence and a motion scheme for which we wanted our cam and follower to operate underneath. Now what we're going to do is using a displacement diagram information, we're going to take that information from there and translate it to now the actual cam itself so that we can construct the profile based on that motion that we identified. Okay, so we're going to look at section 9.6, and that starts on page 237 in our book. And we're going to start first with cam nomenclature or vocabulary, if you would. So figure 918 is what we're going to focus on here. So as we look down at the bottom of that first column where we see the diagram, and focus in here, where we see the diagram of our cam, which is rotating about its center here at the center of the where the shaft would come through. And then you'll notice that we have a follower. It's an offset roller follower that is in contact, and it's going to be moving linearly, okay, as that cam rotates. So as this cam rotates around, there's going to be this, lobe that kind of comes out in an eccentric lobe, and as it comes around, it's going to be pushing out our roller, and then continuing to be in contact. As it comes around, it's on its smaller portion, it's going to be going back down. So it's going to go in and out, and one revolution is going to be the full prescribed motion that we want. So we've looked at kind of that sequence, okay? Now, as we kind of see what's going on here, you'll notice that we have what we call the base circle. Now, the base circle is the one true circle that's on here. And the base circle represents the bottom or the zero of our displacement diagram. So if we were to create a cam that was just a circle, that's going to be our base circle all the way around, that cam would just sit in that one spot the entire time. Okay. It's kind of like if we would take from our displacement diagram and we would take this baseline right here, that's the base circle. Okay. That's exactly what that is. But that's not how a cam works. So it starts out on the base circle, and that's kind of like its home position. And as we rotate, you're going to notice that we start to go further and further away from that base circle. Now, those distances from that base circle are going to be measured from our displacement diagram that would have been created based on the motion sequence that we wanted, and then also the motion scheme. So like if it was harmonic or cycloidal or the constant velocity and such, okay? And it's going to then be in the appropriate time, the appropriate angles, and then come back around to zero to start all over again. So as we move out here, so for instance, if this is my home position, I'm going to say at 90 degrees, okay? This distance right here would correspond to, now it's not going to be to scale here, but if I would count out 90 degrees, it would be that same distance, okay? And then it would translate over to the corresponding distance for whatever angle we're at, okay? Now, as we move around, you're going to notice that there's also a prime circle. Now, in the case of a roller follower, we always mark off that prime circle, which would be the center of where that roller would be if it would follow just the base circle, okay, and not move. And then from there, we mark off the differences to where the new follower location would be. And those distances would then correspond to wherever we're at angle-wise and how far underneath that curve, what that distance is going to be, okay? And then we just basically mark those points off, and we use a spline in AutoCAD to make a best fit curve all the way through there to determine the profile of that cam. Okay. So let's go back to our PowerPoint. So home position is going to be that orientation where that 0 degrees starts. So it's kind of like the 0 degree mark, and then also the base of that base circle point. Okay. The prime circle, as we said earlier, is going to be drawn through the center of our our follower roller center. And then that pitch curve is going to be the path that follower actually takes. That's not on the actual base circle or just around the base circle. And again, it says use the distances from that displacement diagram to transfer to the corresponding angle on the cam. Okay. Now, as we look at the most kind of elementary or entry level cam profile, we're going to have to know exactly what type of follower we're going to have. And the first one that we have here is an inline knife edge follower. So the inline knife edge follower is the simplest one to construct. And as we turn the page to page 238, we will see this process kind of unfold, if you would. Okay. So I'm going to kind of show both things here. At the top of the page, we're going to see a displacement diagram. And what they've done here is they have marked off every 30 degrees of cam rotation. They are showing what those differences are going to be, and we're going to then see how they correspond to the distances on our displacement diagram. Now, if we know that our cam is going, in this case, a clockwise direction, so it's physically going in a clockwise direction, we actually lay out the angles in the opposite direction. Okay, and it's because, and it'll make sense in a little bit, as this rotates around clockwise, it's going to hit that 30-degree mark over here. So we're not going to start 30 degrees clockwise this way. We actually start in the opposite direction because this is going to rotate and then 30 degrees will be here. Okay, so if we're clockwise direction, our angles are going to go counterclockwise around. All right. Now, because this is an inline, that means that we look at the follower and its motion. In this case, it's going to be a linear motion going vertically. Its 0 degrees are going to be in line with the center of rotation of that cam. Okay, and then to mark off our 30 degrees, we go right from the center here, and you're going to notice 30-degree increments all the way around. Now we're using 30 degrees just because we're going to be graphically or manually laying this out, and 30 degrees is enough. The more points you go around, or the closer that those angles are going to be together, the more refined and smooth the actual curve is going to be, and it's going to be more precise. But you'll get the idea with 30 degrees. If you're really curious and you want it to be real perfect, I encourage you to do more, but you don't have to. Okay. But if you do any less, then it doesn't even, represent it as well. So 30 degrees is a nice number. So we're going to stick with that. Now, as we look around here, you're going to notice from the base circle, the corresponding, it's called delta R30. So that's going to be our displacement at 30 degrees. So we measure from our horizontal 0, and we're going to go up to the line, the displacement curve at that 30 degrees. And we're going to find that distance. Okay. And then we're going to take that distance, and from the base circle along that 30 degrees, I'm going to kind of scooch in here, you're going to see that there's that little delta R. Now it's not to scale, but it would be, corresponding distance. Then we're going to go to our 60-degree mark. We're going to find out what this distance is. Here's my delta R 60. And then now I'm going to take that, and along that line right there, this distance right here will correspond to that value that we measure on the displacement diagram. And we continue to go around until we get all the way back to 360 degrees, or back to our 0. Okay. So again, if we're going in a clockwise direction with our cam, our angles are going to be marked off in a counterclockwise direction. Okay. Now, when we actually go through, I'm going to show you on AutoCAD, because sometimes if you haven't used this command before, you maybe don't know where it's at. So to find the spline command, you're going to go over in the draw area, but you're going to arrow down here, and all the way over on the left side, there is spline fit. Okay. And spline fit works where you're going to pick the points that you want to go through. And then at the very end, don't hit escape, because sometimes we end a command by using escape in AutoCAD. You have to hit the enter key for this one. Otherwise, if you hit escape, it's going to disappear, unfortunately. So make sure that you hit enter at the end of this command. Okay. And I'll do a demonstration a little bit later on using it, but that's where it's going to be when we do our construction in AutoCAD. Okay. So simplest one. So now we're going to now look at an inline roller. Now, before we do, I did find just a very simple illustration that I added to our inline roller follower page and our slide. And I'm just going to click on this. And this gives you an idea of the roller being in line with the rotation of the curve. Not exactly sure why there's a little heart on the side there, but there is. Evidently they love this particular one, but I'm going to start back over. But you'll notice that that center line would go and translate right through the center here. And then it has a roller that's in contact with the profile of our cam. And then we see our follower translate in a straight line linearly, in this case, up and down. Okay. So let me get rid of that and go back over here. So that's the very same thing that we see in this scenario, but a little bit different shape of our cam. Now, when we go around this time, using that very same type of an application where we translate the distances from our displacement diagram over, you're going to notice that the construction looks very similar. The only difference is we have an extra circle around here, which is called the trace circle. Okay. But our lines are still coming from the center of rotation. And in this case, again, we have that cam going in a clockwise direction. So the direction of the angles is going to go counterclockwise. And then instead of marking off from the surface here, we actually mark off from that trace circle, because then we're going to be drawing the roller, and that's going to represent its center, this new distance right here. We're going to draw the roller each time around the outside. Now, the difference in the construction here is that when we go around the circle, instead of taking actual points and using our spline, we're actually going to take tangency points along the outside. So in AutoCAD, if I go back over here, in AutoCAD, when we do that spline then, and I know this is actually an offset, notice that we're going to catch the tangency points on those rollers as we come around. Okay. And so instead of using points along, you can do one of two things. You can either go down to your object snaps and take everything off except for tangent, or you can do a shift right mouse button and catch tangent each and every time, or you can use the toolbar here and use tangent each time as well. I believe the most efficient is to change your running object snaps to just tangent, and then that way it's only going to focus on tangencies as you go around, because there are however many, 12 of them to do. Okay. So those are going to be tangencies on those inside portions of each one of the roller positions that you create. But otherwise, very same construction as far as transferring the distances. And this time it's just going to be to the centers of the rollers instead. Any questions on this one? This is going to mimic one of the homework assignments that you have. Okay. The other homework assignment that you have is going to be laying out this one, which is a offset roller cam profile. Okay. Now here, there's just one, kind of a little difference here. So you'll notice that we have our offset distance, okay, from the center of rotation. And then what we're going to be doing is we're going to be creating what we call an offset circle. Okay. Offset circle. Now we're going to start with our 0 degrees here. That's going to be our first position. And that's going to be 90 degrees or perpendicular right here to that center of that offset circle. Then we're going to, from the offset circle, do our 30 degrees. And then from there, 90 degrees offset. Okay. Then we're going to do our 60 degrees and then perpendicular offset, and so on all the way around. Do you guys kind of see that construction there? Okay. All right. Now, once we have those in position, our trace circle is going to go around the outside. Now, this is not in proportion. You're going to notice we have our base circle, and then we have our trace point and our trace circle going, the prime circle going all the way around here. Okay. There's more, it's offset. There's more distance on the right than there is on the left. That is not correct. This prime circle would be exactly the same distance away as that distance is right there from the center of rotation of that roller. Okay. So this is not a good, so if you're looking at this, like, wait, mine should be offset. No, it shouldn't. No, it shouldn't. This drawing is not quite right. Okay. So you're going to follow that same procedure all the way around, and then your offset distances are going to be on our projection lines for each one of our angles. So here's our offset, and that's going to be from the displacement diagram at 30 degrees, at 60 degrees, 90, and so on. And then on AutoCAD, this is the one, actually, this is the homework assignment that I did for you guys, or I did, and I'm just kind of showing you. I wanted to make sure that it all came out okay. Now, something that you're going to notice, because we're going at 30-degree increments, I'm going to zoom in here. You're going to see these little lines. They're not going to be perfectly. You're going to do tangent points, but remember, a spline is going to be a best fit through those tangency points. The more angles we would have in here, so if we would go to every 10 degrees, we would see that be less and less and less until it would be, almost perfect and precise. But this is enough. Okay. You get the idea of the construction. And so if you're wondering, like, wait, this mustn't be right, it is. It's just because we have every 30 degrees as opposed to anything closer together. Okay. So, so that is that type of construction. Now, going forward, okay, so that's, we're going to want to reference that. That's going to be the second homework assignment you have, and you only have 2 CAM profiles to do. Enough. Okay. So, so as we go forward, then, if you are ever curious or whatever wanted to use this for reference, here's the construction for the flat-faced follower. And then there's also one for a pivoting follower. Okay. A pivoting follower. So, but I don't have those assigned for you guys. So let's go back to our PowerPoint presentation. Oh, and I do have an offset roller follower. Let's take a peek at that. Just, it's actually, I think it's like a half-hour video on how to construct this in SolidWorks, but the first 30 seconds are the part where it shows the illustration. So I thought that would be nice. So this is going to be that offset. So you can see that the center line of the motion of that follower is offset. There's a distance between to where the center of that rotation is. Okay, and that's it. What was that? There is, I think it was the last time, I hope I mentioned it, that gives you that quick return option. So when you're offset, when you go around your work, if you need a quick return, for instance, if you're only doing, if you would work or the main motion on the outward portion, then what's going to happen is you're going to get like a quick return type of an action on the other side. So it comes back quicker. Oh, did you? Oh, good. Oh, cool. Yeah. Yeah. They're very useful for, different things that you couldn't get across with just a plain linkage. So, so you can get really creative with cams. So yeah, so I encourage you to, YouTube is amazing. You can find so many cool things on here. So, so anyway. All right. Pressure angle. This is the very last subject that we have here. So pressure angle is going to correlates the follower to the cam pushing force and the side generated within followers. I don't know if I said that correctly, but anyway, the pressure angle is going to be when we look at the center of rotation to the point of contact on our cam, and then we look at where the follower is actually, its action is actually occurring, we're going to see that there is an angle. Now, pressure angle is only going to be in effect when we have an offset cam. If we have a follower that is in line, its its contact with the cam and its pushing force is always going to be going through the center. Okay. So if we look here for an inline cam or an inline follower, you'll notice that as this rotates around, our pushing action will always be through that center of rotation. So there is not a pressure angle when we have an inline type of a follower. But when we have an offset follower, and they show it here, when you are offset from that center of rotation, and you look at through your follower where you're actually pushing, which is going to go through the center of rotation, there's going to be an angle then that's created there. Okay. And you want to try to keep that angle to a minimum. And they say not to exceed 30 degrees. Now, there is a little bit of variation there. It's going to depend on speed as well is going to come into play there too. But trying to keep it right around or lower than 30 degrees is a good idea. Otherwise, you risk that cam not being in contact or jamming up with the actual cam itself. Okay, so pressure angle. I think there's one or two questions that asks you to estimate that for the steepest one that you're seeing as you're looking at your cam profiles. So that, I believe, takes us to the very end. So that means that you are now ready to complete all the homework for this particular module. Okay, so kind of broken up in two sections. The first section is doing displacement diagrams, and the second part is going to be doing cam profiles. So let's take a look at your homework. Back over here. So assignment number 7 corresponds to module 7. So you've got 4 homework assignments. We've already looked at the first 2, which were displacement diagrams, and these last 2 now are going to be our cam profiles. Okay. So we're gonna look at 39 and 41. 39 and 41. So at the end of the chapter here, starting on page 255, okay, we've got 39 down here at the bottom of the second column. So you want to make a plate cam must provide the displacement shown in figure P937. That's on the very next page. So you do not need to generate a displacement diagram. It's already done for you. Additionally, what they've done is for every 10 degrees, they're giving you the follower displacement, but you're creating your cam on every 30-degree increments here. Okay, so 0, 30, 60, 90, those are going to be the numbers that you're going to use. Okay, do not do this every 10. It's too much. Every 30 degrees. Okay, and this particular one is going to be an inline roller follower. The roller diameter is 1 inch. The cam must have a base circle of 3 inches, and it's going to rotate clockwise. Okay, graphically construct the profile and estimate the largest pressure angle. Okay, so this is going to look identical to this setup right here on page 239. Your base circle is going to be 3 inches in diameter. Your roller is going to be 1 inch in diameter. And you're going to start right here at your 0 position. And the cam itself is rotating clockwise. So it's rotating in this direction. So you're going to construct it just like what you see here. Okay. Every 30 degrees. And then your 30, 60, 90, 120 increments are going to come from the top of page 256. You're going to use this chart and you're going to go every 30 degrees and plot that displacement coming back all the way around. Okay. Then the next one that you have is going to be number 41. Now, number 41, this is a plate cam again. This is an offset roller. The follower is positioned in a vertical plane, contacting the top of the cam. The offset distance of 3/4 of an inch to the left of the cam center. The roller diameter is 1 inch. The cam must have a base circle of 3 inches, and it rotates clockwise. Okay, graphically construct the profile of this one. Now, this one is a little different than what we see in our illustration. So on page 240, The only difference here in this setup is that our offset is on the right. In the problem, the offset is on the left. The offset is on the left, okay? So my AutoCAD diagram reflects that offset. So here, you'll notice that here's my 0 degrees. I'm offset 3/4 of an inch to the left. So this is my 0 degrees here. And then I start, because I'm going in a clockwise direction, my 30 is going to be here. Okay, it's going to be counterclockwise. And then my line is perpendicular. And then 60, 90, 120. Okay. And then you do the offsets perpendicular. And then you'll notice that through here, this is my prime circle. It is offset from, you know, it has the same center all the way around. Okay. And then to get those offset distances, what I did was every time that I had an offset, how can I say that I did it? I did an offset. And for instance, for that first, I'm going to do the 90 degree so that we can actually see it. So the 30 is going to be tiny. 90 degree is a 1/2 inch. So to find the 90 degree, if this was my 0 right here, 30, 60, 90 is right here. Then from this circle, I did 0.5 was my distance, and I offset to here. And then you'll notice that's the center of my circle. Okay. And then what I did is I did an offset individually each time, and then I deleted it right away. Otherwise, there's going to be like a million circles going around there. Okay. So I offset all the time from that trace circle. All right. So this would have been if it would have been going all the way around and stuck at that base circle. Now to go around, and once I get all of my circles, my rollers around the outside at each one of my angles, then to get this spline in place, okay, what we're going to do is we're going to use the spline fit, and I'm going to start with, now I always do shift right mouse button, and I want to do tangent. Where's tangent? There it is. Sorry, let me get here. Spline. Now let me go down, and let's change my object snaps to only be tangent. That's going to be the best way to do it. And then I'm going to go to spline, and it's going to find those tangencies. Turn my ortho off, find the tangency, and so on. And so on for every one of those points. Okay. All the way around. And once I get back to the beginning, and it's going to look a little wonky here for a little bit. Once I get back to the beginning, then push your cursor so that it kind of doesn't like go over on the top of itself. And then try not to get anything. Sorry. And then just hit enter so that it sticks. Otherwise, if you hit escape to end the command, it won't, and you'll have nothing there. And then you're just going to need to trim and get a I shouldn't trim that away from before. What was that? It is being mean. See? You know what I'm gonna do? I think I gotta regen, because sometimes it is being mean. I'll play with that a little bit later. But anyway, you'll notice that as we went around here, even when it did the fit through those tangent points, the best fit spline is going to overlap a little bit, and that's totally fine. And to get that better would be to add more and more, increments of angles in there. So that's going to be how you construct it. Any questions as you're kind of, looking at this? It's kind of a matter of doing it. It takes a little bit of time. I encourage you, you'll notice that I use some different colors, line styles, all that kind of stuff. That did make it easier to look at. And I also got rid of lines as I was done using them. Okay. So that otherwise there's just like a craziness of circles. Okay. All right. Any questions virtually? Kind of open up the chat here. Okay. Crickets, that's okay. That's all right. If not, then I am gonna let you finish up our homework assignment tonight. I'll be here to answer any questions that you may have. And then yeah, let me know if you need me.